Hello everyone, this is Professor Ma, and this is the sections on the introduction to the graphs of rational formulas or rational functions. We had the graph of first degree. I know you've seen it many times. Straight lines, second degree, the, the parabolas. Then from here, we start talking about polynomial that's factorable. It'll be some number times x minus some number to some power, and then you repeat this pattern and to some power, and so on. And then we have this undulating, well, that's not really good. Basically, it's an undulating curve. Here's x, here's y, and they go out to infinity. And what else can we extend this graphing patterns? Well, now let's try to extend this into graph of fractional functions. Okay, that is the x in the denominator. To understand or to see how we graph these, the one thing we should understand is what I call how do we visualize the plotting reciprocal positions in the y position. So here's the line y equal to 1, a very important boundary. So if I take a point down below and let's say call this point A, and let's say this is A, let's say this is 1/2, okay? And what's the corresponding positions geometry if I were to flip the y into its reciprocal? Okay, so this is y into 1 over y. And if it's 1/2, then it's going to become 2. So it's corresponding positions of the reciprocal point. I'm going to just call it the reciprocal point, reciprocal of the y point. It's going to be the same a coordinate, but the y coordinate is going to be 2 over 1. It's going to be above y equal to 1. And if I were to do this again, and suppose I choose a point, say B over here, and like say it's even lower, 1/3. That in this case, that its reciprocal point, it's going to be flipped even higher. Because it's going to flip up to B 3 over 1, or B 3. And in particular, if the points I'm looking at is getting, the y becomes smaller and smaller, and their reciprocal point plotted will be higher and higher. So it's there, and so these are the reciprocal points. And what I obtain is, if I connect the dots, it will be a bunch of points start going off. And of course, if these points is y0, then suddenly I find out that is impossible to have. And that at that line, it's impossible to reciprocate these points. So the corresponding points on the line, therefore, never touches this blue line. And that line is called an asymptote. Okay? And this flipping is very important. One way to approach how do we graph rational functions. Okay. So the first assumption is we assume that this rational formula is factorable, and not only that, it cancels all the common factors. So it's reduced. So the vertical asymptote, just what I said, if I take the y equal to x and reciprocate it as 1 over x, and then if I plot it point by point, and as x gets closer and closer to 0, the y become bigger and bigger, 1, 2, and begin to flip up. Okay, and so I get a point, so I get a curve that flips, goes to infinity. positive infinity. Okay, and let me take a second, contrast these with a line y equal to x. What I'm saying here, if I look at the line y equal to x, it's this line right here. And as x become closer and closer to the order 0, their reciprocate, again, this is a line y equal to 1. And the reciprocal of the points getting close to 0 gets to be higher and become higher and higher in the y coordinate, and they shoot up. So as they come into 0, the curve shoots up positive. So this association of the graph of the reciprocal of a graph going through 0 corresponds to going up or goes down along the asymptote. Okay, so this geometrical association, if you grasp that, it will help a lot in graphing. Will make graphing rational functions simple. Okay. Oh, on the negative side, the only difference is the y value becomes more and more negative, so the graph goes down. Because 1 over x, if you do the sign chart, and the sign chart will tell you it's plus over here on this side, and it's negative on that side. So the graph on this side goes downward, below, and the graph on this side goes up. Okay. So this is an asymptote around 1 divided by an odd power of x. Like, for instance, this looks like 1 over x, like this. 1 over x cubed looks like these two, 1 over x to the fifth. Because what we just went through, the principle of the graphing is exactly the same. The graph will be more and more misshapen in some sense, more and more drastic in some sense, but it retains the basic behavior. Now, what's the even power? What even powers is the only difference between even and odd powers is around even power 1 over x squared. Is everything is positive. So when y is when x squared is reciprocated to 1 over x squared, and x squared is very small, 1 over x squared very large, very high. So I've got this chaining when x becomes very small. Squaring it, make it even smaller, but you're going to reciprocate it, so it makes it bigger. So, and here's a graph of x squared. Let me just plot it. X squared looks like that. Okay. X comes in towards 0, and their reciprocal began to shoot up. Remember? They go up. And the same behavior happens on the left-hand side as x becomes, gets closer and closer to 0, and their reciprocal points resides way up because they're positive, and they're positive large number as reciprocal. So therefore, I get this asymptote around the 0, which point in the same direction. If I put a negative sign around the whole formula, of course, then I'm talking about these two lines approach the asymptote in the same manner, going downward. Okay. Now, how do we put these together in graph or to extract the graph of rational formula? Well, first, let's look at the 4 different cases around the different sign around the different extra odd power or extra even power. These 4 different cases depend on positive and negative, right? So the reciprocal of 1 over x minus 1 over x flip over 1 over x squared minus 1 over x squared. Okay. Now, how do we use this to help us to graph in general of any rational factorial. The first thing we do is the same thing we do with polynomial, is we graph the outside of the formulas, the global version. And what's a global version? Well, if I have a formula, okay, let's come. Okay, here's a global version. Basically, to see what happened globally, the outside, I remove these terms because they're insignificant, just like for the polynomial. And then what I have left is a very simple division of power to the x, and therefore all a and b are just two numbers, and the only thing I really care about is plus or minus, whatever. It's a number, it's a positive, be negative, two versions, that's important. Okay? And then I cancel the power of x. Okay? And then I come to the following conclusions. Okay? After clearing all this out, three situations emerge. Okay, disregarding this, only look at that. And if the power on top is bigger, and then after I cancel, I will get like y is roughly equal to like x to some power, because m minus k power. Okay, and basically it is polynomial. Okay, resemble polynomial. And we know what polynomial look like. It looks, one go up, one go down, like that. Or maybe one goes up, one goes down. There are four versions from previous sections. Well, if they're the same power, that means I can cancel them. Then the same power. The only thing left is this constant a divided by b, and that's a horizontal line. Okay, in that case, that's the outside pictures. Then the other case is the bottom has a bigger degree. Then these when x become very large, this line actually become the y-axis, because for large x, 1 divided by large x is very close to 0. But this is what's happening outside. So, and basically, what's happening to the outside of the rational formula is exactly the same things. The way we decide for polynomial, that is the head of the formula determined. Except for fraction, you have two heads, so you have to divide it out to see which one is the real head, the top one or the bottom one, and then that's what the picture outside will look like. Now we come to the middle portions, okay, the portion which we're going to have this asymptotes. And here, okay, first we factor it, okay, and here is a easy version to think about. We're going to think of it, if you remember this formula, and if you think of this as a polynomial, that is this formula. If I factor it, this factor is x squared, max minus 2 squared, and the bottom is x plus 1 x minus 1. If I think of this as a polynomial, then what I have is these are all zeros, and in fact, a lot of students make these mistakes on the test. They treat this like a polynomial. They say, oh, okay, these are the zeros. I will get a curve goes like x minus 2 is a second degree, therefore it goes like this. The sign chart is going to be plus x minus 2 squares plus up there, and that, then it's minus here. Oops, sorry. Let me redo this. It's plus, then it's going to be minus in between here, and then you come back to plus. So if I were to graph this as a polynomial, x minus 2 squared times x plus 1, x minus 1, the graph would have been looked like this. It goes like this, like a square, second order, so like a parabola, goes up, cut through, cut back. If this is a polynomial, but now it is not, what do? Oh, we put these two terms, x plus 1, x minus 1. What do we do to it? We reciprocate it. We put it underneath. We divide by it. The sign chart is still the same sign chart. But what happened to the curve? Here's what happened. Everything over here is pretty much this, in some sense the same. Is this now becomes asymptote. And these also become asymptote because I cannot have x plus 1, x minus 1 in the denominators. Okay? And therefore, for the curve, what does it change in terms of this curve locally around that point where, well, it changed. As they're going to be reciprocated. So that means the curve is going to begin to go up for the fractional reciprocal versions. And similarly on the other side, because if I reciprocate, they're going to go down, and therefore the curve, what it will do is I have to bend it so they start going down. In other words, they have to do this along the zero. Okay. And the same thing on the other side of the other asymptotes. That is the points on this side, they have to go downward because you have to reciprocate them. So they become asymptote at the point, and the points on this side, they have to go reciprocated. Originally, for the polynomial, they go to 0. For the fractional function, no, they go up that way along the asymptote. Okay. I know it's a little messy, but here is what the conclusion is. The graph has to go up asymptote along here because positive, and it has to go down this way. It's asymptote because negative, and that because this is positive. Well, positive, negative, positive. So this side is positive, positive. So the curve make a little. Okay. Here's a sign chart. The curve goes, make a little parabola around 2. And the asymptote forces the middle portion go down, the y become more and more negative, and then finally to the left-hand copy, it goes up because it's asymptote positive. And horizontal outside, what does this curve do? Well, simplify the top and bottom highest degree term, and that's equal to 1. So in other words, as this curve comes out, it gets closer and closer to 1. So when you finished, and this is the graph, and if you graph it, that's roughly what it looks like. Okay. Good practice to do this is, which I didn't put on these. Here's another example. Okay. Go through the same line of reasoning of graphing fractional formulas. One type of formulas that which I wish you to graph upon the homeworks is, let me write it out over here. you should be able to graph y equal to a linear function bx plus b over cx plus d. So for this function, you should be able to graph exactly where the zeros is and where the asymptotes is at, and if it goes up, if it goes down. Where's the horizontal asymptote? This is the one of the simplest case. Okay. So that's it, and have good day, and okay. Bye bye.